Welcome back. Let us resume with our discussion, and before that I can once again check whether we have any questions. V out min. No, what I am saying is V out min, the minimum value it can acquire is close to 0 total. So this is, I would say, the sorry. Fair. No. So yeah, so gate voltage VB. Yes. So corresponding to that, what is the minimum voltage you can have at the output? That is VG of this minus VT. VT is also close to 0.4, 0.5 volt. So it can go all the way close to 0. So why I have written VG equal to 0.4, 0.5? Because VT is close to 0.35 or 0.4. Therefore, if you are assuming that the current is small, the VGS will be close to VT, little bit higher than VT, and as a result, the gate voltage is going to be close to this 0.4 volt. And as a result, the minimum output voltage you can have is there is a VG minus VT, which is close to 0 or few tens of millivolts. Any other question before we proceed? So this DC biasing conditions for the common mode feedback is important. How we are determining the amplifier topology, the reference points, reference bias is crucial. Okay, so now let us talk a little bit about the compensation. We have already discussed the concepts of compensation for the single loop as well as common mode, the dual loop common mode feedback. Let us address some of the questions that were asked, so that the design examples are a little bit more clear. So you have the first loop given by the error amplifier over here and the first stage differential amplifier, and what we suggested is that in order to compensate that, you can use a CC between the gate of this PMOS and the VO plus VO1 plus and minus. And in the common mode half circuit, the way it appears is it appears between the input and output of this common source stage in the equivalent common mode half circuit. So in the equivalent common mode half circuit, remember, we tie these two drains together, gates together. So this becomes a common source amplifier with input as the PMOS device and the drain voltages as the output signal, and the CC also appears between the input and the output of this common source stage. And therefore, at this point you get a mirror multiplied capacitance, and that appears over here, and this is going to push the capacitance or push the pole over here at the output of the error amplifier to low frequency. And likewise, if we look at the other loop, for the other loop, once again we have the input coming from the output of the second stage. So output VO plus, VO2 plus, VO2 minus are coming at this split pair, and the output is going to the NMOS gate. Now if I look at only the second loop and apply a open loop analysis, there I am assuming that the common mode feedback of the first loop is operating well, and it is giving you a stable DC point over here and hence a stable DC point over here. So these two will become AC ground, and I can forget about the first stage and only look at the second stage along with the error amplifier, which is catering to the second stage. So in that condition, the assumption is that the first stage is completely stable, you do not have to worry about it. This therefore becomes DC bias, and in the overall analysis I can put this at AC ground. Therefore, the second stage PMOS becomes an active load and NMOS becomes a input device for the common source amplifier. And therefore, if I just for the sake of completeness, if I draw this, I have my original the error amplifier the way we have just drawn. This is going to the NMOS stage, and for the common mode operation, once again we can tie these two together. These two nodes will be tied together. Therefore, these two PMOS and NMOS becomes overlapped, and we have an overall common source amplifier with NMOS as an input device and PMOS as load device. The gate voltage of these two PMOS is going to be AC ground, because they are coming from the previous stage, the first stage, and that is a fixed DC bias. So therefore, the gate voltages of this become AC ground, and our output is taken at this point, which is coming back to the input. So, in the common mode, once again we can tie these two transistors together and club them into a single transistor, and their input is basically coming from the output of the common source stage. So, while opening the loop, once again I can apply a DC potential over here, set it to AC ground, and apply a test voltage over here and look at the final signal over here. So, this is what we have done earlier for the first stage. And in this case, again, if you want to compensate this loop, we will be looking at placing a capacitor between the output of the first stage and output of the second stage. So, that is what we do in Miller compensation. So, again you can put a CC2, let me call the previous stage 1 CC1 and this is CC2. So, we are going to put a Miller compensation between the output of the error amplifier and output of the second stage. So, in the differential loop, if I draw it in the actual circuit, you are going to have a capacitor between the output of the error amplifier and the output of the two stages. And just to be accurate, if I am combining these two capacitors in parallel for the common mode half circuit, CC2 over here will combine to give you 2 CC2. So, actually this should be 2 CC2, that is just to keep the numbers correct. So, but structurally this is how it is going to appear in the differential circuit. It is going to appear between the output of the error amplifier of the second stage CMFB and the output of the second stage in our overall amplifier. And as a result, once again it is going to compensate the pole of the error amplifier. It is going to result in a large Miller capacitance at this point, which is going to push the pole over here at this high impedance node towards low frequency. So, this is the overall compensation scheme is same as what we have discussed for the differential amplifier based on Miller compensation, where the lower pole is pushed towards lower frequency because of this large Miller multiplication, and the second pole is pushed towards higher frequency because of the impedance of the effective impedance of the second stage dropping at high frequency because of this CC. So, that is what happens, and we have seen what is the effect of that in overall compensation and stability. Apart from this, of course, we have seen for the differential operation, once again I also need to make sure that there is a compensation capacitor between the output of the first stage and output of the second stage. So, that is going to be there for the compensation of differential response. So, if I look at the CC for the differential response, it appears between the output of the first stage and the second stage. That is going to push the pole at the output of the first stage for the differential response to low frequency. That is the purpose of CC. And however, we also need to make sense of this entire thing, that in presence of CC, my overall loop response for the common mode, for the first common mode as well as second common mode, is not getting disturbed. It is same as what we expect. So, just for a check here, if we look at the first loop in presence of CC, what is the impact on the first loop or for the common mode feedback? Likewise, for the differential compensation, when we are looking at this differential response and counting the effect of CC, what is the effect of the other CC value, CC1 and CC2 on the differential response? That also we need to be aware of, so that while designing we can make sure that the CC1 values and CC values are chosen such that the differential response, the target differential response for the bandwidth is also met and the common mode response is also met. Now, if we look at the first loop of the common mode feedback, is the CC over here going to significantly affect the first loop common mode response? So, if I look at the half circuit of the first stage for the common mode response, let me draw the half circuit of the first stage only. Input, let me number this is your M1, M2, 3, 4, and you can have 5, 6, 7, 8. So, now I am going to combine this 1 and 2, this is 1 plus 2 and this is 3 plus 4, and you have the this is your M5, I guess I can call it M9, so let it be 9, and then I have my error amplifier. I can just denote it by symbol, and the reference VCM ref, and this is how I have it. And then I have the compensation capacitor. Once I have opened this loop, I had basically I can apply the input over here also, and I had the capacitor between this input and the output, and also I have the second stage connected. So after this, in the differential response as well as in the common mode response, I have second stage also. So if I draw the common mode half circle for the second stage, I can once again club these transistors like M8 and M5. So on both these sides I can join M8 and M5 and M7 and M6. So I can call it say 8 plus 5, and here I can call it 6 plus 7. So this is the second stage, and I do have the CC appearing between the first stage and the second stage. So the CC for the differential loop compensation I have between the output of the first stage and the second stage, and this one, the first one that I have drawn is CC1, which is for the compensation of the first common mode feedback loop. Now here we said that okay, CC1 is going to have a Miller multiplication, and therefore at this point at the output node you can have an overall multiplied Miller capacitance. So for example, if I open the loop over here as we did in the earlier analysis rather than this point. So in this analysis we can say that the CC1 is going to lead to a Miller multiplication over here, and therefore this output of the error amplifier gives you a dominant pole, and so this pole is going to be pushed towards lower frequency, and this stage is going to act like the second stage of my two-stage op-amp, just like we have analyzed the two-stage op-amp where we put a compensation capacitor between the first stage output and second stage output. So, it is basically acting like the CC between the first stage output and the second stage, and this is giving you a Miller capacitance over here. What about CC? So, if I am putting a common mode signal, after breaking this, if I am putting a common mode signal over here, and it leads to sub signal over here, and you are also having another signal over here. So, is the CC going to play any role in this loop? If I assume that the second stage is controlled by a separate common mode feedback loop which is stable, that means if there is a common mode signal coming over here, the second stage will be able to track it, and it will make sure that the common mode signal over here has not changed. It will make sure that it is remaining constant equal to the common mode reference value which is provided for the second stage. So, this remains equal to VCM ref 2 because this is being dictated by the second common mode feedback loop. So, by analyzing the first common mode feedback loop, I can assume safely that this point is going to remain constant at VCM ref 2. If it was not constant, then definitely we would have the CC coming between the output of the first stage and the second stage, and as a result this would also receive Miller multiplication, the CC times the gain of this stage. As a result, not only this point, but the output of the second stage in the first common mode feedback loop would also experience a large Miller multiplication and hence loading at this point for the common mode response, which would mean that both the poles have been shifted to lower frequency, and therefore the target of having a 45-degree phase margin would not have been met. But that is not happening because we are assuming that the output common mode of the second stage is being dictated by the second loop, and it is fixed to the VCM ref. Therefore, even if you change a signal over here, this is not having any fluctuation because this is being dictated by the common mode feedback loop of the second stage. So, as a result, the CC will not experience any multiplication. CC would experience multiplication for the common mode only if any excursion in this signal would produce a much larger excursion over here. Then only the Miller multiplication comes into effect, because a small change in voltage over here produces an overall terminal voltage across the capacitor which is much larger, and for that you need to supply much larger charge on this side. But that is not happening because even if you there is a small signal excursion over here, this is remaining constant. Therefore, that multiplication factor for the CC is not going to come. So, we can assume that the effective capacitance coming over here, it will be just CC, because this is remaining constant, therefore, AC ground. So, whatever capacitance CC you put for compensation of the differential loop, it will appear as it is between this point and AC ground. So, that is not achieving a Miller multiplication which is going to disturb or push back this loop also, this pole also towards low frequency. So, I only want that for the common mode feedback of the first loop only CC1 should be or the pole over here should be pushed to lower frequency, not this one. I expect that this pole should be pushed towards higher frequency because of the overall impedance of this node reducing. So, you should be able to visualize the combination of this error amplifier and the common mode half circuit of the first stage as a 2-stage op amp, which you are compensating with the help of CC1, and as a result of which it is pushing the pole at the output of the first stage of this effective op amp to low frequency, whereas the second pole over here is getting pushed towards high frequency because of the impedance of the second stage dropping at high frequencies, as we have discussed earlier. Remember that impedance looking into this node becomes approximately 1 upon GM of this PMOS transistor, and as a result it shifts towards higher frequency, the pole shift towards higher frequency. So, this is an important point, you should be aware of this, that CC is not interfering strongly with your common mode feedback of the first loop. Any question related to this discussion? In fact, you can check this in the simulations. What you can do to check this is, if while opening the first common mode feedback loop, if you keep the second common mode feedback loop intact, keep it operating, then you will see that you will be able to obtain a good phase margin by the help of this CC. But if you turn this common mode feedback loop off and just try to bias it with a constant DC, then this signal is going to have swing, because of the applied common mode signal over here, both the outputs will have common mode swing, and as a result this CC will also achieve a large Miller multiplication, and hence this pole will also move down towards low frequency, and therefore it will fight once again with this pole, and then your phase margin will not be achieved. So, you can test this in your simulations also by activating and deactivating the common mode feedback of the second stage while testing the stability of the first stage common mode feedback loop. And remember, when you are deactivating a particular loop, you have to make sure that the DC bias point at this point is close to what you had in the closed loop condition. That is something you should make sure. Any question? So, if I likewise look at the second loop, so if I am looking at the second loop, once again the DC point over here is being determined by the first stage, and we are assuming that this DC potential over here is fixed relatively, and that is dictated by the first common mode feedback loop. So, while analyzing the second common mode feedback loop, we assume that these two DC points are fixed, and hence the gate voltage DC points are fixed, and as a result once again the CC for this stage also comes just as it is, right. So, from this point this is seen as an AC ground. So, while analyzing the second loop common mode feedback and taking the effect of CC2, the CC for the differential operation also comes between this point and AC ground. It is not going to have any multiplication as such. Of course, it is in the reverse path, from this point to this point you do not have gain. So, as such you should not get confused about the multiplication of CC2 anyway, but even then we can see that this point is going to be relatively constant because it is being controlled by the common mode feedback of the first stage. So, while you are opening this loop and looking at the stability of the first loop while keeping the common mode feedback of the first loop intact and looking at the stability of the second loop, there once again the CC over here just appears as it is between the output of the second stage and AC ground. So, if we recall our common mode half circuit of the second stage, where this is the second stage of my op amp. So, here you will have CC appearing between this point and ground, it will not have any multiplication as such. So, again CC is not significantly interfering with the compensation of my second common mode feedback loop, it is just appearing as an additional load capacitance over here. and in general the second stage will also have load capacitance because of the next stages. So, when you are applying multiple stage of amplification, this will also face load capacitance because of the next stage. So, anyway you will have a CL over here, which is detected by the input capacitance of the next stage amplifier, which can be significantly large, few picofarads as we have seen in our examples. Therefore, this is anyway having a pretty large load capacitance, which can be larger than CC, significantly larger than CC. So, this is definitely not affected much. Second loop is not affected much by the CC. First loop, you can say that yes, in the first loop at least you are having an additional load capacitance provided by this compensation capacitor for the differential compensation. The second stage not so much, because it is already having load capacitance which can be significantly larger as compared to CC. So, apart from that you may anyway have CL, which is much larger or significantly larger than CC. And we can also look at the reverse picture, that whether the differential mode operation is affected by the CC1, CC2. So, whether the differential feedback, the differential compensation is having an interference because of the capacitance that you have put for the common mode feedback. So, once again for that I will look at the input signal applied over here, and I will be looking at the output signal VO2 plus and minus. I can use the capacitive feedback and look at the voltage division coming out of that also, as we have discussed. In order to look at the A beta, you need to look at the capacitive division also. So, from here you will be connecting those two capacitors and tapping the center point, and that will give you the A beta factor, that is for the loop gain. And then we can check the overall differential half circuit. And for the differential half circuit, if I assume that the input signal is anyway differential and the common mode gain of the circuit is poor. So, at these points you will have effectively differential signal coming, even if the input signal that is acquired from the sensor, it is having asymmetry, right. So, if you remember our discussion, the two electrodes that are coming, they are taking the signal in the vicinity of a certain area of the brain, and they are kind of close together. So, they are not acquiring exactly same signal. They are signals can be relatively different, and you are trying to process the difference between those two signals. So, at least at the first stage, if I see, they are the input signals are not fully differential, but even then if I assume that the common mode rejection ratio is good, the common mode signal coming over here will be much smaller as compared to the differential signal. So, the signal over here is fully differential, and for the differential operation, the signal that you get over here is close to 0, right. So, because if these two signals are differential, the signal over here will be summing up to 0. As a result, this CC1 and CC2 will anyway appear between this point and AC ground. Sorry, the CC1, the two CC1s over here will appear between these 2 point and AC ground, because we are assuming that this point is constant or stable, because common mode signal over here is not sufficiently large. Even if there is some minute common mode signal, it is not sufficiently large that it disturbs this point significantly. Because if there is a large common mode signal over here present over here, then of course the common mode loop will come into action and will try to stabilize the output common mode level over here to the same value, and as a result you may get some signal coming at this point. But if I assume that as in general the common mode signal is going to be very small, this is going to be more or less constant and hence AC ground. Therefore, CC1, both the CC1s appear as it is. So, for the differential half operation, for the differential half circuit also, while doing the frequency response, you will have to treat this CC1 as load capacitance or additional load capacitance coming at the output of the first stage. Likewise, if I look at the CC2 over here, they are also following the same argument that overall differential signal over here is large, but as a result of this, the common mode signal over here is not going to be very significant, because if the signals over here are differential and common mode at the input is not changing significantly, then the output point, output DC point, bias point provided by the second common mode feedback amplifier is also going to be relatively constant, and as a result this is going to appear more or less as a DC bias point and hence an AC ground for the differential operation. As a result, the CC2 also appears as it is between the output and AC ground. So, it basically can be clubbed with the load capacitance that you have for the differential operation, and as I said, the load capacitance can be significantly larger than the CC2 that you get. So, for the differential response, once again these CC2 are going to appear between the output point and AC ground as it is without Miller multiplication, and they can be clubbed with the load capacitance. So, once again they are not interfering so much with the frequency response of the differential operation. Only thing is that when you are compensating the differential response with CC2, sorry, the CC over here, you have an effective CC1 also coming over here, and intentionally if you try to make the bandwidth of the common mode loop small by putting a large CC1, then you have to make sure that the CC that you are putting over here is taking into account the CC1 that comes over here for the differential operation. So, as I said, in general you may like to keep the common mode response or the common mode bandwidth low. It is not required to be high because it is just catering to DC bias, unless the signal is supposed to have a very common mode signal which is sufficiently strong. So, unless that happens, I would like to keep the common mode bandwidth. I can afford to keep the common mode bandwidth smaller, that can save me some bias current. In some application you may need to keep the bandwidth of the common mode loop also similar to differential case, in case you have significant common mode disturbances coming and there is a chance of getting these output common mode for the first stage and second stage getting disturbed. So, in that case you may like to track it closely, but in other case, say as if your supply voltages are very stable and you do not have much of a common mode disturbance coming in from other sources, we can afford to make the common mode feedback relatively lower frequency, and in that case you may go for larger CC1 and CC2, and in that case I have to make sure that the effective CC1 coming over here for the differential loop is not really you are accounting for that CC1 while choosing the value of CC for differential compensation. Any question before we take a short break? There is another small point related to again another query that was asked for alternate ways of compensation. So, probably we will be looking into that briefly. So, before that, any issues related to whatever we have discussed over here regarding the compensation for the differential and the common mode loops, the two common mode loops and the differential loop and their interaction.
Sir, in this differential operation, will the load capacitance introduce any phase shift that is unwanted?
As I said, load capacitance will lead to an overall effective loading, and then in order to calculate the poles at the output, you have to basically rely on that load capacitance plus this CC2 that comes into picture. So, CC2, as I said, is also appearing as effective load capacitance, especially if you are trying to make the common mode loop slower. It is appearing as an effective load capacitance because this becomes an AC ground for the differential operation. So, ultimately the choice of CC depends upon the load capacitance. The choice of CC for the differential operation depends upon the load capacitance. So, compensation depends upon the load capacitance because that is determining the output pole. Output pole of the second stage depends upon GM upon CC, GM of the output stage divided by CC, and therefore, of course, it affects the phase margin. So, depending upon CC, total effective CL only, you have to determine the CC. So, in this case, you have to just keep track of the discussion that we had in the last day, where we talked about opening the loop in simulations and how to do the bias while keeping the DC points intact at different points. So, for the dual common mode feedback loop also, you have to make sure that while you are opening the loop for the DC or the stability analysis for these individual loops, and then for the differential loop, the DC conditions are remaining intact. And while you are opening one loop, say the first common mode loop, the other two loops are intact, or while you are opening the second common mode feedback loop, the other differential loop and the first common mode loop is intact. So, those considerations you definitely should be able to make while doing simulations. Likewise, when you are doing differential simulation and trying to assess the stability of differential operation, you would like to keep the two common mode feedback loops intact, so that they are taking care of the DC biases of the output node. And input node, we had some special consideration that we discussed that day.
Sir, for simulation point of view, if we for a phase margin, we determine first CC1, then again CC and CC2. So, after
there are two different loops. So, CC1, CC2 can be pretty close. So, these values are just to stabilize these two feedback loops, and amplifier configuration bias currents are similar. So, they can be pretty close. CC can be different because of the bandwidth requirement. You can have a different pole for the differential operation as compared to the common mode operation. So, if you are, for example, trying to keep the bias current in this error amplifiers lower, in that case the bandwidth over here will be lower, and you can the compensation after compensation you will be getting a lower pole over here. But for the differential operation, you may have bandwidth requirement, signal coming is much faster. You would like to maintain a probably larger bandwidth for the differential case. So, that will be the main concern which will be which will let us choose different values of CC, CC1, CC2. So, CC2 and CC1 can be close, because these two loops are common mode feedback loop and their speed response demanded for a particular application may be close. CC can be different because the response sought by the differential loop can be faster. For example, if you have to say compensate the feedback, differential feedback considering the capacitive division. So, as I said last day, your differential feedback is having the capacitive division. As a result, the loop gain is the A1, A2, that is GMRO square order times the beta factor, which is small, maybe 1/30 or 40. So, that already gives you better stability for the differential loop as compared to the common mode loop, where you have the overall loop gain given by GMRO times GMRO, that is just maybe 30-40 times larger than the differential loop. So, compensation for the differential loop can be easier if I consider that beta factor, and then the required CC value may also be smaller. So, that can make a greater difference. In some cases, you want to be aggressive and conservative. So, you will try to compensate the differential loop also for the worst case, that okay, because of the parasitic effects at higher frequency, the beta approaches 1, that will be the worst case, and therefore, I will consider the loop gain of the differential case also to be GMRO square, then the CC value will be large. But you can take the advantage that for the differential loop you have beta factor, and that is reducing the open loop gain overall. The overall loop gain is getting reduced by the factor of beta, and hence you can afford a smaller CC for the differential case. So, that will allow you to compensate the differential loop separately and the common mode separately. When we use same common mode loop for both the cases, then we are relying only on one CC to compensate both, and in that case it is basically tied with the larger gain GMRO square gain that is obtained for the entire loop, and that basically leads to over compensation of the differential loop. That is what we discussed last time. So, let us come back and we can discuss the dual loop, I mean a single loop case, and try to look at another interesting point that was raised in last discussion, and also contrast the pros and cons of the single loop case with the differential dual loop case. We will resume our discussion and try to finish the comparison between these two. So, and arrive at some conclusions regarding the choice of single loop versus dual loop.